Hi guys, welcome to episode 5, CAD from Sketch to Parametric. This episode is not about teaching you every button in SolidWorks or Fusion. This is about how we model like a real STEM racing team, not like chaotic homework. By the end of this, you should know what CAD tool you're using and why, the 3 core modeling principles we follow on this program, how to assemble parts into a full car, how to name parts and keep versions under control, how to learn fast without getting lost, and how not to break a machine or your fingers when it's time to manufacture. This is the backbone of how we go from idea in your head to a legal and buildable car. So first, let's start with the mindset, from sketch to model. The sketch is where you define your basic proportions, reference planes, center lines, mounting locations, axle locations, cartridge positions, and wheel envelope. Don't worry about pretty surfaces yet. The 3D model is just the 3D version of that intent. If you jump straight into 3D without a plan, your model becomes impossible to edit later. And every change breaks 5 features at once. If you lock your core sketch first, then everything else is built off clean references. Now let's talk about CAD platforms, SolidWorks and Fusion. These two are the mainstream softwares that most people use on the market. We're going to talk about both, but I'm not going to tell you which one is better. You should decide based on what you can actually get trained on. I concluded the upsides and downsides for both softwares, and they are on the slide. Me personally use SolidWorks since I have some previous experiences on it. And I think SolidWorks surface and features are more intuitive, especially the material database and SolidWorks CAM. However, it doesn't run on Mac OS, but Fusion does. So if you only want to model on MacBook, Fusion is the choice. Also, you can find free student account of Fusion on STEM Racing North America's team portal. So just pick the tool where you can get support, training, and file sharing with your actual teammates. If 3 people can help you in Fusion and 0 can help you in SolidWorks, use Fusion. If your mentor is a SolidWorks god, just do SolidWorks. Now let's get into modeling fundamentals. This is the 2D to 3D method. Think like a fabricator. If you want material, you extrude it. If you don't want material, you cut it. So step 1, make a 2D sketch on the base plane, usually a main reference plane like front, top, or right. That sketch includes real dimensions. Step 2, extrude that sketch into a 3D solid. Step 3, make another sketch on another plane and cut away what you don't want. Extrude to add, cut to subtract. That's basically 90% of early part modeling. Do not overcomplicate early geometry. Focus on controlled dimensions and references, not cool shapes. If your base sketch is clean, editing later is easy. If your base sketch is chaos, every single edit in the future will be painful. Okay, let's apply that into an actual car. Before you sculpt the final body, you build what we call a skeleton. Here's the 3-rule mindset for modeling a race car body. First, skeleton first, then features. That means you should start with a skeleton sketch that defines wheelbase, axle center lines, max allowed width, cartridge chamber center line, tether line position windows, and critical safety geometry. The skeleton is your true source. You do not freestyle off the surfaces. You build surfaces off the skeleton. Second rule, assembly structure plus reference planes. From the beginning, thinking assemblies. The car is not one block. It's chassis, body, wheels, axles, tether line guide inserts, cartridge mount area, halo, and a lot of parts. Each of those should have reference planes that should line up in assembly. Don't guess locations, you should define them. Rule 3, parametric variables. Don't hard code numbers if you plan to tune them. Things like wing thickness, mounting angle, wheel spacing shims, ride height pads. Make those driven by parameters so you can change one variable. and update the geometry everywhere. If you follow those 3 rules, you can iterate without fully rebuilding the car every time. Okay, now let's talk about assemblies. So this is about how to mate parts together. We are building towards a full car. In CAD, an assembly is just a group of parts locked to each other using relationships. And just like what's listed on the slide. And here's what that means for us. Wheels should be aligned coaxially on their axle center line. Axles should sit at the known right height plane relative to the track reference. Things like that. When you do this right, the assembly behaves like the real car. When you don't, you end up forcing parts together in the shop because CAD said it fits, but CAD was lying. Numbering and versioning. If you standardize names, anyone in the team can open the folder and know which part is current. And you can roll back if version 4 breaks. I listed some ways of categorizing parts here. Using these ways, someone can look at a drawing and immediately understand what kind of document and version it is. And then for CAD file names and revisions, we're going to use a consistent rule shown on the slide. Next, learning path. This is how you can get good in CAD fast. There are 3 ways. First, find tutorials online. Watch SolidWorks or Fusion Basics on YouTube, specifically for sketch constraints, extrude and cut, assemblies, and parameters. Don't waste time on insane surfacing tricks on day 1. Peer help is also a good way. Sit next to someone who already models fast. Ask them why, not just where do I click. You can also learn by doing something. Pick one real sub-component, like a wheel spacer or tetherline guide insert, and model it clean, fully dimensioned, fully named, with a drawing. Then hand that off to manufacturing as a test. Your goal is not be a CAD god today. Your goal is to be reliable and readable for the team. Okay, now, safety before manufacturing. This is super important. CAD makes parts look real, but on a CNC mill or any power tool, you can actually hurt yourself or destroy the machine. So before any physical manufacturing, the tool path must be checked and approved by a teacher or supervisor. Fixturing and work holding must be secure. No loose hands holding stock. And also, you do not just let it rip because Fusion CAM said it's fine. Treat manufacturing like a controlled process, not an experiment. Because at the end of the day, the car matters, but you matter more. Thank you for watching. In the next episode, I'll introduce the aerodynamics and physical design philosophy you should have for STEM racing cars. I'll see you in the next one.